Up to now, we have assumed that we had a single gaseous substance, but a key property of a gas is that the molecules are far away from each other and do not interact. As such, the precise nature of the molecules is not really important. Quite frankly, all we care about is how many molecules are present in the container holding the gas. Assume we have a mixture of gases, A, B, and C. All three substances occupy the whole container. In other words, all three gases share the same volume. The same can be said for the temperature. All three gases share the same temperature. However, the pressures are additive. Each gas is said to have its own partial pressure, the pressure it would exert if it were alone in the container. The total pressure is just the sum of the partial pressures. Dalton's law simplifies calculations. If you want to know the total pressure, one need only worry about the total number of moles of gas. If you want to know the partial pressure of a gas, one need only worry about the numbers of moles of that one gas. In other words, the famous PV equals nRT can be applied using the total number of moles and the total pressure, or it can be used using the number of moles of an individual gas and its individual partial pressure. You pick the one that is applicable to the problem at hand. In experiments, Dalton's law is often used to find the pressure of an individual gas being generated and collected over water. We can measure the total pressure, but we have to keep in mind that the gas being collected over the water contains both the gas we want and water vapor pressure. Dalton's law tells us that if we subtract the pressure of the water vapor from the total pressure, then we have the pressure of the gas being generated by the experiment.